All right, happy Friday. So end of week 3 here. So I want to talk about the ODPs, the one you just did and the one that's due tomorrow morning. No ODPs over the weekend as usual. I'll post one Monday morning. So I want to go over the ODPs, and then I want to start talking more about hash functions and hashing and look at some details of that and start working towards some pseudocode for implementing hashes. And I'm leaning towards PA3 is going to be related to hash functions and hash tables. But we'll see where we get and what my mood is. So any questions before we jump into all that? How's PA2? Cool. I would like to think that most people have either finished or are seeing the end in sight.
I think I'm at least halfway done.
Okay, awesome. Please do not wait until Thursday to begin. Right? Hopefully in PA2, if you did that, you discovered that some of these things take time. And PA2 is a different mindset to manipulating some of this stuff. So ODP 209 was looking at removing a node. So we're deleting the middle node from this linked list. So here's what our list looks like, and we don't know what's stored in these nodes to begin with. So I'll just draw question marks there as placeholders. But the goal is to remove this middle node. So when we're done, we'd like our list to look like this. And when you do these assignments, right, if it says remove a node, that's really what you want to do. You want to remove a node. You don't want to, for example, copy this into here and then remove that third node, right? And you definitely don't want to simply make a new list containing that and that, right? We really don't want to manipulate things that we're not asked to manipulate. That's going to be really important as we go forward, because a lot of times these things are going to be fairly complex structures, and if we do something like say, well, let's just get rid of that third node and copy the data value over here, we can get into trouble. So we really want to just sort of change this first thing to point to the third thing. So one way to do that is something like this. So I used a temporary struct node pointer, so I wouldn't have to think too hard. And I called my argument n, so I'll relabel pointer to also be n. And I said temp equals n arrow next, and n arrow next equals temp arrow next. So what is that doing? Temp equals n arrow next. Well, this is n. N arrow next is this next node. And I'm avoiding putting the little line under there and putting in the top and bottom sections. I'm just thinking n arrow next is this. So temp, I'm just going to write down, is this node. And n arrow next, that's what n points to, should be whatever temp is pointing to, temp arrow next, which is this. So I'm saying this should point over to here. And that gives me this picture here. N is actually pointing to two things. It's still pointing to temp, but it's not pointing to temp. It's pointing to this next thing. But temp is still pointing to this node that's removed from the list. So that lets me say free temp that returns the block to memory. You didn't have to free for the assessment. You'll get full credit with or without that. But if you're going to free, you probably need some kind of temporary. Because if I do this, if I just do this, so n next equals, and instead of temp I could say n next next, right? Single line, have n point to the thing that n points to. That sets up this link. But once I do that, I have no way of getting to this node so I can free it. If I were to say free n next is not this node anymore. I just worked really hard to make n next equal to this node. So if I free n next, I'm freeing this third node, which is part of my list. And so you might say, well, okay, we can fix that. Here's n. And I'm going to say n next equals n next next. And we just said we can't free n next after that because n next is now pointing to a different node, so I'm going to free that first. Well, the problem is, as soon as you free something in memory, think of that as no longer available. So if I say free n next, this no longer exists. It's gone. Not part of our world anymore.
And the list is broken.
And the list is broken. And now when I say n next equals n next next, n arrow next, I don't know what that is. It used to be pointing to here, now it's pointing to a big purple blob. And whatever that purple blob is pointing to, that's what I'm going to set n to point to. And now I'm potentially making my list point to somewhere bizarre. So don't do this. And don't do this. So kind of have to use a temporary, either for this node or for the thing that you want to point to.
Was it safe to assume that the last node in the list was null, pointing to null?
I think that's what it said. I don't know, did it?
I don't know.
Yeah. So it was a list with exactly 3 things in it.
So is it safe to assume that the next ODP has a similar setup where the last node points to null?
No. But it shouldn't make a difference. So ODP 210, again, a list, no sentinel node. You're writing a function edit2 that gets 2 things. It gets a number and it gets a pointer to the first node. And your goal is to squeeze a new node in between the second and third nodes. So this should turn into that. And there's no assumption about what the data values are here. There's no assumption about whether this is the end of the list or not. But neither of those should really affect your code, I don't think.
Well, good news is it doesn't. I got full points.
Okay, cool. Awesome. So yeah, create a new node, and it's just pointer manipulation. The rest of this course is just pointer manipulation, in some sense. Because loading the data value, creating a node is just a call to malloc. Setting the data value is just new node arrow data equals num, right? The trick is the pointer manipulation. And in this case, you need to find where this pointer is, and instead of pointing here, point to a new node. And then have the new node point where this thing used to point. Okay, you've already done this in PA1, but you weren't using arrow notation, you were using arrays. But it's the same algorithm. So you have to somehow remember where this is pointing, make your new node point there, and then have this point to your new node. That gives you a list that looks like this. And then you return the actual pointer, so that's just going to be returning whatever you were passed. So you're past this struct node pointer, that's going to be your return. Oh, actually you don't return anything. Never mind. Because you don't ever change that, so just return void. All right, so other questions on 210, 209? All right, so let's talk more about hashing. So I want to get really comfortable with this idea of a hash function, right? Remember the high-level view of what we're doing. We're taking pairs of data, a key and a data, pairs of items, and we want to store these into a pair of arrays, a key array and a data array. And the goal is, here's a name, here's their office number. And we want to be able to associate these with one another. So instead of storing these in sequential locations in our arrays, which is expensive to search for, we use this function that we call a hash function. Here's a key, tell me where to store it. Oh, that key is Izad, store it at location 17. Now I want to store Bob. Okay, store that at location 5. And the goal is that if we want to find one of these things, I'm looking for Bob's office number. Okay, check location 5. Go into location 5. There's Bob. Oh yeah, okay, their office is 12. So this is built around the idea of a hash function. So we pass it a key, and it gives us an index. And the first problem that was jumping out from this was the possibility of collisions. So the idea that two or more keys might return the same index in that function. And we can only store one thing in a particular index. So we introduced this idea of a probe. So our hash function takes two arguments. It takes the key we're hashing, and it takes an integer, which is a probe number. So the first time we try to hash a key, we're going to use a probe of 0. If you get a collision, rehash with a probe of 1. If you get a collision, rehash with a probe of 2. And so on until you find a spot that's not in use, and that's where you're going to store your key and your data. So we can couch that in the language of a function by saying this hash function now takes two arguments, the key and the probe number. Start from probe number 0, and it gives us a different index depending on what that second argument is. So we looked at a very kind of naive hash function, which was take the name, the key that you're given, look at the first letter. If it's an A, return a 1. If it's a B, return a 2. If it's a C, return a 3, and so on. So here's what this function might look like. So if we ignore the probe for a moment, just simple hash of a name. This is pseudo code. So get the first character of the name, just name bracket 0, I'm going to call that car. Subtract 64 from its ASCII code. That's just magic. So an A will give us a 1, B will give us a 2, Z will give us a 26. Right? ASCII code for A is 65, so this would give us a 1. And they go sequentially after that. Okay, and then we could just return end. So if we're looking at Izad, we're going to get a 9. If we're looking at Nick, we're going to get a 14, and so on. But there's this problem of collisions. right? So if we try to convert Carol into an index, we're going to get a 3 for C. If spot 3 is occupied, we want to try spot 4. And if that's occupied, we want to try spot 5, and so on. So what we can do in here is just say index equals index plus probe. So the first time that we hash, let's work with Carol some more, right? Index is going to be equal to a 3 for the letter C. If we call this with a probe of 0, we're just going to return 3. If that collides, we're going to call it with a probe of 1, we're going to return a 4. If that collides, we'll call it with a probe of 2, that's going to return a 5. And so on. So each time that we call this hash with a new value of the probe, we're going to end up with the next possible location in our table. So this is called linear probing. And it's fast to implement, but it's not very good because we get this clustering effect. If we hash a bunch of people whose names start with C or D or E, they're all going to get jammed up together around this beginning part of the array, and the rest of the array may be very underused. A better hash function is one that's going to distribute things throughout the table. And more generally, a good hash function, if you have two inputs that are pretty close to each other, if they look similar, if they differ in just a small amount, you'd like them to take you to different places in the hash table instead of just coming in really close. This is chaos, right? You make a small change in the input, you get a big change in the output. Chaotic hash function is great. Okay, one that's not chaotic is not very good, because if your data happens to be clustered, the place you're going to try to store it is going to get clustered. All right, so this is a simple hash function. It's using linear probing. A second possibility, instead of doing this, we could add the square of the probe. That's quadratic probing. Why is that better? Because by the time we get to our fifth hash attempt, or our fourth hash attempt, we're going to be taking the original location we tried and we're going to move down 16 spots from there. Right? First we're going to try at some location, then we're going to try the next location, then we're going to jump down 3 spots to try the original location plus 4, then we're going to jump down 5 spots to try that original location plus 9, and we're moving further and further apart each time that we probe. The idea is if we got collisions the first 3 or 4 tries, there's probably a cluster of things up here in the table, so let's get really far away from that. And quadratic probing will help us do that. Okay, but that's just another example of how we can write a hash function. And there's lots of different ways we can write hash functions. So let me show you a couple of other ones we might use. So I'll just call this hash 2. Take a name and a probe. Well, tell you what. Let's write some code. So we'll have a hash function that takes a string and a probe number, and it'll return an int. All right, so here's my temporary input buffer. We'll read in with an fget. We'll call our hash function. And I'm just going to loop through the first 5 probes. Let's just see what our hash function does. So we'll set the index equal to the hash of that. And we'll just print out the probe number and what the result of the hash function was. All right, so this is just going to test the hash function, and we're going to play around with different kinds of hash functions here. So let's do our simple hash. Typo. All right, so there was our first simple hash. Just take the name, subtract 64. So let's hash my name, and oh, I didn't use the probe number. So we just add the probe, linear probing. Right, so probe first 5 attempts return successive locations, 14, 15, 16, 17, 18. And we pass in Mary, and we get 13, 14, 15, 16, 17, right? So you're going to get clustering here, right? Lots of people with first initials that are close to each other. You're going to get the same chunk of locations that you're going to try. So not a really great hash function. So quadratic hashing. So we try to hash cat, and we try locations 3, 4, 7, 12, and 19. Okay, less chance of clustering. So that's a step in the right direction. So let's add up the ASCII codes. And we'll use quadratic probing on this also. So we'll do our standard for loop. If you don't have this, if you're not writing this in your dreams, you will by the end of 222 or 223. So that's just a standard for loop, go through each character in the string, and in this case we're adding them to a running sum. So we'll do quadratic probing, and our numbers are going to get really big here, right? So I'm going to assume that we have 101 locations in our hash table, so we'll reduce the result modulo 101. So we'll always get something from 0 to 100. And then we'll just return that. Alright, so let's try that. So here's cat, and we get probes of 88, 89, 92, 97, and 3. Here's Carol, and we get probes of 2, 3, 6, 11, and 18. And here's Caleb, and we get probes of 77, 78, etc. Right? So taking us to different spots in our table. And if we happen to collide, if we get someone else who was already in location 77 and 78, right, we'll end up in location 81. Here's an issue, though. So if I use cat, it probes to that. If I use ACT, it probes to exactly the same locations. If I use TAC, it probes to exactly the same locations. Right? Why? Because we're just adding up the ASCII codes of the letters. Now, do people's names have the same letters in different orders? Not usually, but other sets of data, this might happen. And so this might be a poor hash function because of that. So what could we do? We could take the ASCII code and multiply by I plus 1. And now we've got position dependence. So now cat starts at 85, TAC starts at 51, ACT starts at 87, and so on. So you can get very fancy with your hash function. Depends on the nature of the data. We're not going to spend a whole lot of energy in here learning about how to write a particular type of hash function for a certain type of data. Right? There's scientists who do that for us. We just want to understand the basic concept, which is we take a name and a probe number, it gives us an index. For reference, here's an MD5 hash. So MD5 hashes take arbitrary strings and convert them into 128-bit numbers, 32 hex characters here. And for example, if you take this string, quick brown fox, it hashes to this. If you add a single period to the end, it hashes to that, which is very different. If you have a totally empty string, it hashes to this. Right? Our system, if we had an empty string, it's not actually empty, it's a new line, character 10, so it hashes to that. But if it was truly an empty string, it would hash to 0. And that's not a really good thing to do to an empty string because it's kind of an edge case. So MD5 is a hashing algorithm that takes input and gives you back this 128-bit result. Now it's not something you'd use as an index into an array because we don't have arrays that are 2 to the 128th entries long.
But then you have to also convert from hex to int.
Yeah, you have to convert from hex to int, and that's a big int. But we can use this, for example, to take an arbitrarily long input string, say a text, a book, and convert it to a 128-bit number. And we could have this 128-bit number that uniquely identifies every book in the world based on its contents. And if you go in and you add a comma to one sentence in the middle of page 500 and you rehash, you're going to get a totally different code. And it's a more or less unique mapping from every book ever written to this single 128-bit number. And this is useful for a lot of things, including security. So you go to the library and they don't have the book that you need, so you go down the street and there's someone with a van and they say, hey, I'll sell you a book for $2, right? And you get the book, and it looks a little funny. You're not sure this is an actual copy of the book or if this was just some cheap knockoff, right? And you want to know, am I going to be getting the right material? Well, you could calculate the MD5 hash for that book and compare it to the MD5 hash that the library said goes with their book. And if they're different, this is not the same text. There's at least one character that's different somewhere. Okay, so this is what you do when you download code. You want to download PuTTY. The manufacturer of PuTTY tells you what the MD5 hash should be for putty.exe. You download PuTTY, well, you got it from, yahoo.hackme.com. You run your putty.exe that you downloaded through your trusted MD5 generator, and it gives you an MD5 code. You compare it to what's on PuTTY's site. And if it's different, this isn't the same program. There's something different somewhere. That works under the assumption that two different programs are going to give you two different hashes back. And in general, that's true, but if you're very clever, you can make that not be true. And so MD5 is filled with security issues. it's possible to take a program, add malicious code to it, and add some other stuff so that when you calculate the MD5 hash, it's the same as what the original would be. So that's a vulnerability. So people have known about MD5 vulnerabilities for a while. SHA is a better version of hashing for security that's got vulnerabilities too. Right? It's always a moving target, measure, countermeasure. But that's the idea of it. So how does MD5 work? Well, here's some code for generating an MD5 hash. It's a mishmash of logical operations and other mathematics. And somebody came up with this, and it works pretty well. It's got magic numbers. It's got magic numbers generated by doing trigonometric functions on integers, and so on and so forth. And there's a synopsis of how it works. It's basically take your input, break it into chunks, break those chunks into 4 pieces, A, B, C, D, do these logic operations, XORs, ANDs, ORs, NOTs, and put those together. But in the end, it's just a hash function. And there's no probe number in there, but it's a hash function, takes in the name, gives you back a number. All right, so let's assume that we have a nice hash function available to us, and let's go back to looking at how we use these. So we have an array. It's got some collection of indexes. Doesn't matter how big. It could be 26, could be 1001. But this is like our key array. And there's a parallel array, which is data. We really don't have to say a whole lot about that. All the work happens over in this key array. If you're searching for a particular piece of data, we hash it, we look in here, we move through, we deal with collisions, we ultimately decide, okay, either our key is not in the table, in which case we're done, or our key is in the table at location 511. At that point, we just go to the data array, look at location 511. There's the data that corresponds to that key. So the data array comes along for the ride. We don't have to really do any work with it. All the stuff happens over here in this key array. So we're just going to talk about this from here on out. So there's this idea that we want to store a name. So we store cat, and we try to store Carol, and that goes in the next location. And we try to store Caleb, and that goes in the next location. And we mentioned at the end yesterday that deletions can be an issue. So if we're searching for Caleb, we're going to hash to this location, and that's not Caleb, but there's something else in here. And we know, since we wrote the storage algorithm, that if we tried to store Caleb and cat was already in here, we would have stored Caleb somewhere else. We would have stored it in the next location. So we check the next location, that's not Caleb, but someone else is in there. So when we stored, we might have gone to the next location, we check that, hey, there's Caleb. Okay, if we're searching for Kate with a C, we do the same thing. We check here, Caleb, nope, that's not Kate. But if we had Caleb there when we tried to store Kate, we would have gone to the next location. Go to the next location, it's empty. Kate's not in our table. Okay, but we have to have some way of knowing that this is empty versus occupied. So we added this flag called valid. And we initialized it to 0 everywhere. But when we stored a name, we set valid to 1. To say, okay, somebody's in this position. So that's how we know that we've got a collision. We check the valid flag. All right, so now the trick is when we delete, let's say we delete cat. So we're going to set this valid flag to 0 to say there's no name in that location. But now if we search for Caleb, we hash Caleb, we get to location 3, we check, this spot is empty. We might say, I guess Caleb's not in the table. because this spot is empty. If Caleb was here, we would have stored it right here. That's not a valid conclusion, because when we tried to store Caleb, there was somebody in here. It's empty now, but in the past it was not empty, so we need another flag. And so we're going to add one more flag, which I'm going to call deleted. And we'll initialize deleted to 0 everywhere. When we delete someone from the table, we set the valid flag to 0, but we set deleted to 1. And that's our reminder when we go back to search that there used to be something in here. So now we search for Caleb. We come to location 3, we check that. There's nothing in there. Was there something? Yes. So now we know that when we stored Caleb, we might have had a collision. Let's check the next location. That's occupied. Check the next location. Hey, there's Caleb. So our key array has to have at least 3 pieces to it. It's got to have the key itself. It's got to have a flag of some sort that tells us whether that key is actually a key or just, you know, an empty spot. And we've got to have a way of knowing if something used to be in that spot, so a deleted flag.
Is the deleted flag permanent?
Is it what?
Is it permanent?
Yeah, it's permanent. Once it's deleted, if we store something here, we'll change that to a 0. But we'll never go back to an empty cell with deleted 0. All right, so now let's look at some pseudocode. Let me keep this table. This may be useful. Okay, so let's start off with insert. So let's insert a name. So I'll initialize a probe number to 0. I'm going to hash my name with that probe. And I'm going to say if that entry in my hash table, whatever you call your hash table array, if that entry in my hash table, valid, equals 0, that spot's available. So I'm going to save the name in the key field. I'm going to set the valid field equal to 1. You don't really need to do this, but I'm going to go ahead and set the deleted flag equal to a 0, and we're done. If the valid flag is not 0, that cell is occupied. So increase the probe and rehash. And go back up. So insert, pretty straightforward. Basically keep probing until you get to a spot that's available, and then store your information in that spot. And there's details here, right? One detail is if the table is completely full, we can keep hashing with different probes. We're never going to find a spot that's available. So we need something in here to know if it's hopeless, to know that we've already tried this location, or to know that there's no free spots available. So you got to do some extra stuff to deal with that, but that's an edge case. All right, so that's how we insert. How do we search? Well, again, start off with a probe of 0. Hash that. Okay, if the valid flag is set, it means this is actually a name in here. So if the valid flag is set and the key field is actually equal to the name we're searching for, we're done. We found the name. So we can say, yep, they're found in the table. And we can just return. If the valid flag is 0, meaning there's nothing in that entry, and the deleted flag is 0, what do we conclude? It's not found. If the valid flag is 0, but the deleted flag is set, then we need to try again. Increase the probe, rehash, go back up and try again. Sorry, this is valid equals 1. No, I missed a case. It's not deleted, not found.
We're missing the case where valid is 1, but it's not the name.
But it's not the name, right? Thank you. So we hash, we get to an entry in our table that label is occupied, right? There's something in that location, but it's not the name we're looking for. Could have been a collision, so again, we got to come down, hash again with a different probe. So search has got some cases to deal with, but if you think through what these things mean, right, you should be able to come up with an algorithm that's effectively the same. I keep saying this in the course, right? The code is useless. It's not valuable, right? It's what we were talking about that led us to write down these things. That's what you're after, right? If you understand what the valid flag and the deleted flag do and what hashing does, you can reproduce this, you know, on a desert island without any other resources, and then you can make your Gilligan's Island hash function. Right, so this is just looking at this pair of flags and whether your name matches. So that's a search function. And if we know how to search, we know how to delete pretty easily. So what does delete look like? First, search for the name. So do all of this stuff. And if the name's not found, you shouldn't be trying to delete it anyway, but just, you know, either yell at the user or just return silently. But assuming that you find the name, right, we know where that name is stored in the hash table. We've got the index. So search for the name, and let's suppose it's found at location index. So set the valid flag equal to 0 and set the deleted flag equal to 1, and you're done. So deletion is trivial once you go through all of the search stuff to figure out where the entry is stored in the table. All right, we can add, we can search, we can delete. That's all we got to do. We got to initialize. So how do we initialize a hash table? Go through with a for loop, set all the deleteds equal to 0, set all the valids equal to 0. There's your initialization. So as an abstract data type, our interface to a hash is init, add, search, and delete. The user never calls the hash function. The user doesn't know anything about probes. The user doesn't know anything about collisions or valid flags or deleted flags. The user knows initialize, add, search, delete. Right? That's their interface to all of this stuff. So your main program, if you write a main program to work with hashes, is just going to use these 4 functions. And everything else is going to be magic that happens inside these. And then if you download a package for doing hashes, it'll have its own initialize, add, search, and delete functions. You can just call those instead. And now you got different mechanics coming on underneath the hood, but your program's working exactly the same as far as its functional behavior. Just different implementation. All right, so I will not post new ODPs over the weekend. I will post one Monday morning, which will get us playing with some hash functions. And then hopefully you'll have questions by then. And we'll take a look at some other implementations of hashing, such as DBM, and we'll go from there. All right, so I will see you next time.